the formula work is force times distance. Very easy. So force is we are using the unit in the English unit. We are not using the metric. That's because a lot of general aviation aircraft is American made. So the Americans are still using the English unit. So all the units are going to be most probably in English. But we have some European countries or Australians doing the building the general aviation aircraft. So you must always be careful and always refer to the manual and look for the units, whether it is in metric or in English. Because the calculation, when you are doing it the wrong unit, then you'll get the very wrong years. Okay. So horsepower, that is why horsepower is an English unit. So we must convert whatever that you have in English unit pound, English unit feet, so inches. So they are going to be changed into an older version of the English unit. So power we can refer to as foot-pound per second, and that is the basic English unit. But they are not the older English unit. They cannot measure that. What is foot-pound and per second? They cannot imagine that. So they need to have a comparison. So they are using horsepower. So they can visualize what that kind of power is. And so if you have 1 horsepower, that means you have 1 horse pulling, call it 1 pound of work. Okay, so wait. So let's look at this. So 1 horsepower is the amount of power required to do 33,000. I'm referring to your textbook. Look at the textbook. Look at the arrow. 33,000 foot-pound of work in 1 minute, or 550 foot-pound of work in 1 second. So that is the power a horse can do. So like in the old days, when they referring to power, they are actually measuring the power of the horse, because horse is the animal that piece of burden at that time, and they want to do work. They are going to use animals, and they are not going to use ox. They are not going to use any other animals except for horse. So, so when you have to change the unit of the foot-pound per second or foot-pound per minute into horsepower, so you need to know that one horse can do the work of 33,000 foot-pound in 1 minute. So that is the unit conversion. So that is how you get this formula. See. Okay, so I'm just I'm just reading this. This is what I thought you might have learned in physics. What is indicated horsepower? Indicated horsepower is the mechanical power. When you talk about horsepower, it is mechanical power. So so in combustion engine, we are changing the power constantly, from chemical energy, from chemical power, chemical energy in the petroleum, in the fuel. And when you burn the fuel, it will break the chain of the octane, and they will break the chain, and that chain is actually energy. And you release that energy, so when you have combustion, you will gain heat. Where is that heat coming from? It is from breaking the chain. So from chemical energy, you get heat energy. And then from the heat energy, you increase the pressure inside the combustion chamber, and you are expanding the volume inside the combustion chamber. How? You are pushing down the piston. So from heat energy, you are changing it again to mechanical energy. So horsepower is actually mechanical energy, and that indicated horsepower is the power that is being converted directly from the heat energy. See? So, but if you look in the textbook, okay, what is this pie chart is talking about? The power, I mean energy, energy that is being distributed during the engine operation. So the energy is 45% being wasted through exhaust. See, this is not mechanic. This is not horsepower. This is not mechanical power. This is talking about energy. So from that energy, you can do power. You can do work. When you do work, you can do power. But here we are talking about the energy only. So the energy is in the fuel from the linkages that is linking the carbon atom in the octane of the fuel. So when you break the chain, you will be getting heat energy coming out from the chain, from the broken chain. So that energy is being distributed to become all these items in this pie chart. So 45% of the energy is being wasted through exhaust. Only 27% energy is being used to turn your propeller. And then you have also propeller friction, propeller losses at 3%. And then you have some of the energy being wasted through cooling at the cylinder. And then you will have friction, wasted 5% of the total energy. So only 27% of energy is being used to turn the propeller and producing thrust. Most of the energy wasted through the exhaust. So that is why some of the manufacturers, they are trying to increase the efficiency of the energy of the engine. So they are going to install turbocharger, or they are going to install charger juga. Tapi turbocharger tu usually it is to turn compressor, isn't it? To suck in outside air, to give more air into the cylinder to produce more power. Itu basically turbocharger. Tetapi ada lagi satu namanya turbo recovery. Nanti in piston tu you will learn about this. There is a turbine installed in the exhaust, and that turbine is turning not a compressor but turning your crankshaft. So it is recovering or trying to scavenge whatever energy that they can scavenge out from the exhaust and back, put it to crankshaft, so that the crankshaft can turn the propeller. So the turbine is also changing the heat energy into mechanical energy, and then that mechanical energy is being transferred to the crankshaft. The crankshaft is also rotating, isn't it? Turn the propeller. So some of the manufacturer will do that because they want to make their engine more efficient. For a little bit amount of fuel, you'll get more power. That is efficiency. If you are wasting a lot of fuel, but your power is this much only, very little, so it is not very economical, isn't it? It's not powerful enough. So people are going to reject that. People are going to go for more efficient machine, more efficient engine. Okay, so let's take a look on the example given here in the textbook. And then if you don't understand, you tell me, because this is just a revision actually, this is just from physics. So you plug in the numbers and see whether you can get the correct answer or not. By just referring to the textbook. It's all in there. You can do the exercise. Maybe after the at the end of the chapter also there will be some exercises for you to do it, and then you can find the answers at the back of the book. Okay, so let's move on to volumetric efficiency. Indicated horsepower is the original mechanical power that is being converted, and that is just being converted from heat energy. Heat energy is giving you a rise in pressure in the combustion chamber, and that rise in pressure will push the piston downward. And so when the piston is moving downward, it is going to move. So the piston moving is mechanical power. Understand? So piston moving, and things are moving, mechanical power. When pressure are rising, that is heat energy. Why do we need to measure or calculate the indicator horsepower? Is because we want to know how much actual energy, percentage of energy being transferred in from mechanical energy, from the heat energy to mechanical energy. So that is why we have that pie chart. So normally for piston engine, that is the distribution of the energy being transferred to. So 27% can be for most of the engine, or maybe it is slightly better, becomes 30% for useful work. So it depends on the manufacturer. And then when the manufacturer install also a turbine at the exhaust, then it can recover back all the wasted heat, so to become mechanical energy. So that will increase also the performance of the engine. So maybe it will increase to 40% of useful work. And then you reduce the wasted energy to exhaust to 30%, like that. So in order to find out the percentage, to find the efficiency of the engine, you need to calculate the indicator power, you need to calculate how much fuel is being given for the given RPM. So all that. So indicator horsepower is the original mechanical power, which is where you have the piston moving downward. The piston moving downward at power stroke. Okay, so the power is being produced at the power stroke only, and the piston is going downward. That is the indicated horsepower. Now, if you have 4 cylinders, then you are going to multiply it with 4. If you have only 1 cylinder, then only 1 lah. Let's move on to friction horsepower. Why do we need to calculate the friction horsepower? Same thing, because we need to find out the distribution of the energy from the original energy contained in the fuel. Now it is going to be distributed to where? So indicator horsepower is the original power, mechanical power. And then you have friction horsepower, which is the power that will be lost due to friction. So how do you measure this? That is where you have this. This is what you call the dynamometer. Back in the old days, you will have this. This is the prony brake. Okay, so prony brake, it is not really efficient. They are using wood slab here that will have a friction adjusting wheel, and then you have the engine clamp on to that prony brake right here. So when the engine is running or you are turning the engine, then this prony brake will be pushing down on the scale and giving you the force. So when you have the force, you have the arm, force times distance, you'll get work. So for how many seconds or how many minutes? And so this is how you measure how a horsepower back then for your engine. But nowadays we don't have this. It is highly inefficient, highly unreliable. So nowadays we have this dynamometer. Last time we have dynamometer that is utilizing hydraulics, but nowadays all are electronic, because electronics are much more dependable, simpler, easier, less messier. So no hassle. But in the old days, when you have dynamometer, they can also use hydraulics, which is not as good as using electronic. So nowadays, you can just install the engine here to the dynamometer. When the engine is running, the propeller shaft will be turning a generator. So that generator is going to calculate how much power, how much watt, convert it into horsepower. You'll get the what it is that you want to get. So you want to have friction, you will calculate. One brake horsepower. Brake horsepower is the power to turn your propeller. So we haven't touched on that. Friction horsepower, you are going to, okay, how do you calculate friction horsepower? So how do you measure the friction horsepower? Is by installing the engine, and instead of the engine driving the generator, now the generator is turning your engine. So why is that? Because you want to know how much friction, how much power it takes to turn the engine without the engine running. So the generator is now turning into a motor, and that motor is going to produce how much power to turn the engine in 1 second. So that is how you measure friction horsepower. Ask the motor to drive the engine when it is dead. So that is how you get the friction horsepower. But if you are talking about brake horsepower, now brake horsepower, you want to, you can calculate it. Brake horsepower is the power to turn your propeller. So this is how you calculate the brake horsepower, which is 2 pi times torque times RPM divided by 33,000. Why do you divide it into 33,000? Kalau you tak bahagi 33,000, boleh juga. Tetapi bukanlah unit horsepower. Unitnya adalah foot-pound per second or foot-pound per minute. Jadi kalau unitnya tadi foot-pound per minute, then you divide by 33,000. Kalau unitnya foot-pound per second, you divide by 550. Okay? So it is very simple, isn't it? So let's look at this example. 600 foot-pound of torque, and then the RPM is 2,700. RPM stands for what, Fazil?
Revolution per minute.
Andai. So the unit being used here is minute, not second. So if it is RPS, then it is revolution per second. But now it is RPM. It is minute. That is why divided by 33,000. Because 1 horsepower is actually 33,000 foot-pound of work in 1 minute. Very simple, isn't it? Now, so I've talked to you about the Brony brake. I've also talked to you about the dynamometer. Okay, now we move on to total piston displacement. Okay, so what is piston displacement? Piston displacement is actually displacement volume is measured from the top dead center at the head of your piston to the bottom dead center of the position of the piston at the head of the piston. So this is total piston displacement. It is not total volume. Total volume is not equal to displacement. You understand? Displacement means you displace something, you move something. But total volume is not the same as displacement. Displacement volume is this much only, because this is how much the volume that is being removed or taken in. Okay. So piston displacement is area of the piston head, which is pi r square. Because the piston head is circular, so it is pi r square. Then times L, which is the length of the stroke from top dead center to bottom dead center. That is the stroke, the length. And then how many number of cylinders you have. If you have one cylinder, just multiply by 1 lah. If you have 4 cylinders, you multiply by 4. So that engine will have that amount of air going in and out the engine. So the engine is sucking in and pushing out this much of air. Total piston displacement. If the engine has 18 cylinders, then you multiply by 18. Very simple, isn't it? No question. Yeah, you have question? Yeah, you there?
No, sir. No.
So very simple. Now we move on to engine efficiency. Okay. First thing here is the thermal efficiency. So, like I said before, fuel will have chemical energy. That chemical energy has been measured before. So we found that for gasoline, it is around 20,000 BTUs. Let's look at this paragraph. Look at the paragraph that I'm highlighting right now. So 100 LL aviation gasoline is 6 pounds. 6 pounds per gallon. Each pound of 100 LL aviation gasoline contains 20,000 BTU. Yeah, that is for gasoline. If it is for kerosene, kerosene is being used for turbine engine. So turbine engine, they use kerosene. Kerosene has more than gasoline. That is why most of the turbine engine will use kerosene, because it is much more compact. But the difficulty by having kerosene as your fuel is that it has almost the same specific gravity as water. So you cannot easily separate water from kerosene. That is only the problem for using kerosene. Other than that, kerosene is much better compared to gasoline, because it is much more compact and giving more power per gallon. For gasoline, the water is going to separate very quickly from gasoline, but the gasoline is containing only 20,000 BTU. Okay. What is BTU? British thermal unit. Yes, so by multiplying pounds per minute of fuel by the engine burns by 20,000, you'll get the total number of BTUs or total heat energy. So 1 BTU, okay, this is important. 1 BTU capable of doing 778 foot-pound of work. British thermal unit is actually 1 BTU is actually 778 foot-pound of work. That is why in your calculation, it is stating here, calculation, this formula. Okay. This horsepower is actually either indicated horsepower. Okay. This highlighted horsepower here is actually either indicated horsepower or brake horsepower. So the total heat energy that is being produced is this. This is mechanical power, and this is actually the total heat energy produced by the combustion. And why is this? Why is 33,000 here? So ratio means something is divided by something, and that those somethings must be in the same unit. When you are comparing apple, you must compare with apple. You do not compare apple with pineapple, isn't it? They are different. So when you are comparing something, you must compare apple with apple, not apple with mango or mangosteen. You don't do that. That is not comparison. And so when you want to compare apple with apple, you must have the same unit from the top to the bottom. So the top here, the unit is the horsepower. So you at the bottom here, the unit is in foot-pound per minute. So that is why you multiply it with 33,000 here, so that this horsepower can become foot-pound per minute, same unit as the one. So that is the thermal efficiency. So the what do you call it, the energy, the heat energy is at the bottom because it is the original the source of heat, the source of energy, so it is at the bottom. But at the top you have that horsepower, so that horsepower can be either indicator horsepower or brake horsepower. So that is the power that the heat energy has change into mechanical energy. So either you want to have indicator horsepower or you want to put it as brake horsepower. Brake horsepower is the mechanical energy that is driving the propeller. So that is why you have either brake horsepower, brake thermal efficiency, or you can have indicator thermal efficiency. If you want indicated thermal efficiency, you put here indicated horsepower. If you want brake thermal efficiency, you put here brake horsepower. So this horsepower can be either brake horsepower, or it can be horsepower. And I've told you before, indicated horsepower is the power when the piston is going downward. Brake horsepower is the power to turn your propeller, isn't it? So we have calculation for brake horsepower, 2 pi top times RPM. That is how much power being used to turn your propeller. For indicated horsepower, the formula is this. Indicated horsepower is Planck divided by 33,000. Why you divide by 33,000? Because you want to change it to horsepower unit. So if you don't divide by 33,000, it's still okay, but the unit is foot-pound per minute. So P is the IMEP, the indicated mean effective pressure. So you will have a probe there. When you want to do this calculation, you are going to install probe inside the cylinder, and that probe is measuring the pressure built up during a power stroke. See? And then L is the length of the stroke. You before. You can, okay, this is recorded, right? So you can just refer back. You can rewind the video. And then you have A. A is the area of the piston head. I mentioned this before. And then here you have number of power strokes. So my question is, if the engine is running at 2000 RPM, how many power stroke do you have for that 2000 RPM? Azil?
1000.
Andai, very good. Because 4-stroke cycle engine, it takes 2 revolutions to complete everything. So everything, 5 events there must happen in that 2 revolutions. So if you have 2000 RPM, so you will get 1000 power stroke. So that is one event. You are referring to compression stroke, also 1000 compression stroke. Now we are talking about power stroke, isn't it? And then here K, K is the number of cylinder. Okay. Kalau engine ada 4 silinder, kali 4 lah. the engine has 6 cylinders, you multiply by 6. Okay. But not to be confused with the piston displacement. This piston displacement formula. Piston displacement formula. So if you're talking about piston displacement, the formula N. See N here. This N is actually talking about number of cylinders. Don't get confused. Total piston displacement unit is not the same as the indicator horsepower formula. The N is for different things. Here the N is for number of power stroke per displacement. The N here is for the number of cylinders. But for the indicator horsepower, Planck K is the number of cylinders. Okay, so don't get confused with the formula. And we move on to volumetric efficiency. So we have here how many? We have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 factors. 8 factors that affects volumetric efficiency. So my question is, what is volumetric efficiency? Look at this, the first one. This is a partial throttle operation. So what do you understand from partial throttle operation? So when throttle plate is not completely open. So what is throttle plate? So let me show you the picture. So this is inside your fuel metering device. So the engine will get its air from this fuel metering device. Air will be coming in from outside, passing through screen or filter, air filter, and then it goes to the fuel metering device. So this metering device will have this. This is what you call the throttle plate. Textbook. So this is the throttle valve. This is what you call throttle valve or throttle plate lah. Dia boleh benda yang sama saja. And this is open position. This is what you call full throttle. Full throttle is only this position. Open position. Other than this position, other than this, you will call it part throttle. So if it is in this position, you call it part throttle also. When it is at close position also, it is part throttle condition. If it is a little bit going to close to open position also, it is part throttle position. And only this position, this white color position is what you call full throttle. Other than that, you call it part throttle, like this yellow. So partial throttle operation. So you still remember or not? Part throttle. Part throttle is other than full throttle, isn't it? Mal?
Yes, sir.
So other than part throttle, other than full throttle is called part throttle. When you have part throttle, it means air is being restricted to go in. Okay, so before that, let me just tell you the definition of volumetric efficiency. This is the definition. Volumetric efficiency is volume of the mixture corrected for non-standard conditions divided by total piston. So you still remember what is total piston displacement, right? It is how much air is being sucked in and out through the piston, through the engine. So if the engine has 4 cylinders, how much air is being sucked in by the 4 cylinders? And then we have here the top here, volumetric efficiency for non-standard condition. What does it mean? Non-standard condition 2 are all this: partial throttle operation, induction friction, induction bands, elevated induction air temperature, elevated cylinder head temperature, incomplete scavenging, improper valve timing, and changes in altitude. So all that are non-standard conditions. So all those 8 factors are the volume of feature, non-standard condition. Okay? So now I've talked to you about the partial throttle condition. That is the one of the non-standard conditions. So when you have part throttle, that means the air that is coming in is not as much as full, isn't it? Full throttle. Full throttle means just show you again the picture. Full throttle position, which is the spike position. So other than that, the air will be restricted to go in to your cylinders. So it will be restricted. Only this much air can go through. But it is, if it is in full position, you can see the air that is coming in can go this much and this much. But at full throttle, it will be only this much or this much, or even this much only, this much only. So that is the part throttle condition. So when you have the part throttle to the second one, which is induction friction. So induction friction is very simple. Every surface you will have friction. Now, air flowing through a surface, when air is flowing on the surface, the air will be restricted. Why? Because there is a friction between the air movement and the surface. So the pipe that carries the air to go into your cylinders, it has a surface. So that surface will increase in friction. The surface will increase in friction if the pipe has rough surface, or it has bend, or it is very small. So the friction will increase because of that, because air flow on the surface, it will what you call it, slow down, because it will be slowed down by the surface of the pipe, the inside of the pipe. Okay, so that is induction friction. The amount of friction directly proportional to the length. Of course, if you have longer pipe, that means you are getting more friction. Because more surface to travel, isn't it? Very simple. Small, okay. Long, small diameter intake pipes create most friction, while short, large diameter intake, of course, will have less friction. It is common sense. Move on to induction bands. Like I said before, when you have bending, you need to slow down and corners, isn't it? So like you are driving F1 car, when you are at the corners, you are going to slow down because you need to change direction. So that is also slowing down the movement of your air, and the air will be coming in late into your cylinders. So you are reducing the amount of air into the cylinder. Same thing. Friction also slowing down the movement of the air going into the cylinder, thus less air coming in. Now we have elevated induction air temperature. So if the air is hot, what becomes of the density of the air? Mal.
Yes, sir. Low, sir.
Bagus. So heated gas will have lower density. If you have lower density, you have less mass. So less air coming into your cylinder, reducing your volumetric efficiency because the mass is not there. Very little. How about elevated cylinder head temperature? Elevated means getting higher. And so the higher cylinder head temperature will make the surrounding air, including the air in the pipeline, in the manifold pipe, to become hot. So when the gas and the air going into your cylinder becoming hot, they will reduce its density. So less air also will be coming in. And if the cylinder is too hot, you might have the air that is heated up inside the combustion chamber to flow out and forcing to stop the incoming fresh air. So when it stop the incoming fresh air, you are getting no air at all coming in, and maybe a trickle maybe. But that is how you reduce volumetric efficiency, because not enough cooling for your cylinder. That is very bad. Not only that, but also you will encounter other problems such as detonation to ignition. Later we talk about it. So incomplete scavenging is another problem. If the valve overlap in the engine is incorrect. So I've shown you the power W. This is the power W that I've drawn you before, isn't it? But this one is much nicer. We will have valve overlap. We'll have valve overlap between here and here. It is not stated here clearly. Actually, the intake valve will open here, somewhere there, and the exhaust valve will close here. Last time you remember or not the picture that I've drawn for you? Actually, the valve overlap is between the intake valve and the exhaust valve. They will open together. Not open together, but they are going to be opening at this time frame. From here, that is to allow all the exhaust gas that is in the cylinder, in the combustion chamber, to be kicked out from the combustion chamber. Who is going to kick out the exhaust gas? That is the fresh air. That fresh air is coming from the intake valve. So when the intake valve opens right here, okay, the exhaust valve actually open here, much before that. So the exhaust valve will open here, and then when you have the intake valve opening here, so what will it do is to kick out all the exhaust gas out to the exhaust valve. So the exhaust valve it is going to close here somewhere. So it depends on the manufacturer. It can be 25 degrees, it can be 14, it can be 10. It's up to the manufacturer because they have tested the engine. And so this is the region where both valves are open. It is called valve overlap. Okay, and that is that is stated in the textbook. So incomplete scavenging. If the valve overlap, and when the intake valve will open and also the exhaust valve is already open, in the engine is incorrect. Maybe it is opening too late. Maybe the intake valve is opening too late, or the intake valve is opening too early, or maybe the exhaust valve is opening too late or too early. Then the overlap will be off a little bit. So when you do not kick out all the exhaust gas out from the combustion chamber, there will be some of it left inside. So some that will be left inside is going to increase the pressure of the cylinder. So it is going to prevent fresh air from coming in. So that is a problem. That is why if you have incomplete scavenging, means you do not kick out all the exhaust gas out from the cylinder, you are going to reduce the amount of fuel air charge and the fresh air going into the cylinder. So that is one factor also. And then you have the improper valve timing. If the valve is opening too early or too late, closing too early and too late, then maybe it is not achieving what the manufacturer has already tested. And maybe The time frame is too short. The air don't have much time to fill up the combustion chamber. So that is reducing also the amount of air into your cylinder. Thus, less oxygen meaning less fuel. Less fuel means less power. That is improper valve timing. How about changes in altitude? As you climb up, the aircraft climbing to higher altitude, what becomes of the air density? It will reduce. So the density will become thinner. So that also will reduce your mass to go into your cylinder. So that is reducing volumetric efficiency. Now, this is mechanical efficiency. Mechanical efficiency is very easy. And because the formula is, mechanical efficiency is the percentage obtained by comparing. When you talk about efficiency, it is a ratio. When you talk about ratio, it is comparison between similar units of items. So when you talk about mechanical efficiency, it is a comparison, a ratio. Percentage obtained by dividing brake horsepower by indicator horsepower. As simple as that. If you have brake horsepower, you have the indicator horsepower, divide them. And brake horsepower on top, indicator horsepower at the bottom. Because indicator horsepower is the original of the mechanical power. So how much it is being translated into brake horsepower, that is why we need to do this calculation, mechanical efficiency. Move on to factors affecting power. So we have one, two, then we have three, we have we have five, then we have 6, 7, 8, 9. They have 9. Just affecting power. So the first one is detonation and pre-ignition. Wait, nanti. The first one is manifold pressure. Manifold pressure, factors affecting power. Is pressure just outside the cylinder at the intake port, just outside the cylinder, at the back of the intake valve. So that is where you measure the manifold pressure. There will be a part line going to your cockpit to show you the pressure. The cockpit saying MAP, manifold air pressure. So it is showing you actually how much air that is, how much pressure is present there. So they use call it pressure. But as you know, when the engine is heated up, the pressure is going to increase, isn't it? So actually the density is expanding. So actually to accurately measure how much is the mass of the air, it is depending on the temperature also. And so manifold pressure is only showing you the pressure, not showing you the mass of the air that exists in the manifold pressure. So, but usually when you have high pressure, that means you have more mass, usually. But in unusual circumstances, like when you have too much heat, the temperature is very hot, then the density might be reduced a little bit. But overall, usually manifold pressure will indicate how much air that is present to enter the cylinder. So it is actually showing the mass of the air that is going in, but actually it is not. and because the mass depends on the temperature. So, but anyways, that is the one of the factors that will affect your power. If you have more mass into the cylinder, then you will have more power. Yeah? But like I said before, if the temperature is very hot, then you have high pressure also. Still, the power is not that much. That is because of the density has changed due to the temperature rise. So overall, in all, the manifold pressure is actually showing you the mass of the air. So higher the manifold pressure, the higher the mass. Normally. Now we move on to detonation and pre-ignition. So what is the definition of detonation? It is detonation describes as uncontrolled ignition and explosive burning of the fuel air mixture in the cylinder. Uncontrolled. Uncontrolled means like this. So this is what the normal pressure rise is going to be. And then it is sloping down like this very smoothly. But now when you have detonation, you will have the pressure suddenly rising up like this. Off the chart already, you see. Off the chart, and then it will drop suddenly like this. And then raise up again, and then dropping like hell again. And so the rise and the fall of the pressure will be very irregular. It is jagged. Jagged. Jagged means it is very rough, very sharp. So it is irregular. It is not smooth. If you look at the normal pressure in a normal combustion, it will be as smooth as this. But now you have detonation, it will have a jagged rise and fall of your pressure. So when you have this jagged performance of pressure rising and dropping, so it is going to make a violent vibration. And when you produce a vibration, you are requiring energy. Where do you get energy from? You will get it from the energy that is being converted from chemical energy into heat energy into mechanical energy. So you are getting it from the mechanical energy. So the vibration also is a movement. So vibration is a mechanical energy. So you are going to use a lot of this mechanical energy creating this vibration, which is very bad. Because engine will be rough running. That's why you will hear an explosion sound, a knocking sound in the engine due to this, due to the detonation. So that is uncontrolled. How about pre-ignition? Pre-ignition is you have combustion occurring before the spark plug fires. So that is pre-ignition. What causes pre-ignition? Sometimes you have the spark plug firing at the wrong time. And you set the magneto and later you think about it. So the magneto is set such as the spark plug is going to fire much early or much later. So that is wrong. You must follow the manufacturer's manual. Always the spark plug must fire according to the designated time by the manufacturer. That can cause pre-ignition. Other than that, also you have hotspot. So some parts of the cylinder might be dirty, or there will be accumulation of dirt forming a silicon deposit. and sticking on the wall of the cylinder. So that foreign silicon debris will be the point of hotspot. So that hotspot, it will retain heat from the combustion, from previous combustion, and when they have a fresh fuel air being compressed, combining with the deposit hotspot, then you will have enough energy to combust the fuel air charge. So that is going to occur before the spark plug has the chance to fire. So that is early, pre. Pre means earlier, pre-ignition. This pre-ignition will cause detonation. Why? Because when you have the combustion happens too early, then the piston is keep on increasing pressure, then it will have a very violent rate of combustion. You will raise up the pressure inside the combustion chamber very high, and it will suddenly drop very steeply. And so it will be a jagged rise and fall of your pressure inside the combustion chamber. That is detonation. Okay, so that when you have pre-ignition and detonation, you are increasing power or losing power? Azil? Azil? Yeah?
Yes, sir.
Are you getting more power or less power to propel your propeller when you have detonation or pre-ignition? Detonation. Detonation will perform this kind of graph, which is jagged. It is going to cause you to have knocking sound, a lot of vibration inside your engine. That vibration is going to take away the mechanical energy to drive your propeller. So it means that it is reducing your power to propel your propeller, to turn your propeller. So it is reducing power. Is it good or bad? Very good performance, very high efficiency of an engine. And you don't want to spend a lot of money, but it is producing a dismal, very little power. And so that is very bad. So let's move on to the next one. Okay, this is pre-ignition. The definition of pre-ignition occurs when the fuel air mixture ignites before the spark plug fire. So the spark plug should be firing according to the manufacturer's recommendation. You cannot have the spark plug to fire much earlier than that or later than that. So the setting up of the spark plug to fire is by adjusting the magnitude. Later you learn this in history. So that's about detonation. Okay. So the other factor that affects your power is the compression ratio. So this is your compression ratio. If you have higher compression, do you get more power or not? Ikmal, are you there?
Yes, sir.
In your opinion, what will be a better engine? Higher compression ratio or lower compression ratio?
Higher compression ratio.
High performance cars, usually they have higher compression ratio. Yeah. So sometimes also you have mat rempit, motorbikers, they modified their own engine, their own cylinders by changing the connecting rod, which is this. This is the connecting rod. Make it longer so that the piston can go much higher, isn't it? So that is how the mat rempits, the motorbikers change their cylinders performance, they increase the compression ratio, or maybe they what do you call it, shave off the cylinder to make it shorter so that it can have a more compression ratio. So a lot of things to the motorbikers have modified their engine, but actually the manufacturer has already set the engine at that precise measurement. If you change it, then what will happen is the engine might be easily worn out, or engine will blow gasket or something. You have a lot of problem later. But in terms of performance, you are increasing it, but at the same time, you are going to spend a lot of money, not only by modifying it, but also to make a replacement or repairs. So it's up to you. So higher performance cars, they will have higher compression ratio in. So normally they will use a higher grade fuel. Higher grade fuel means heavier fuel. Like my motor, like my Waja, and my car Waja, it can be using lower grade fuel like 92, like 95. But certain high performance cars like the Mitsubishi, they only can use 97 or 100 at the Euro standard, which is heavier fuel. Heavier fuel means more energy per gallon. So it why is it like that? Why is the low performance cars can use higher grade fuel, but for high performance cars, high performance engine with high compression cannot use a lower grade? Why is that? So the engine with high compression ratio will make the fuel air charge to become very hot. When you pump your motorcycle using hand pump to fill up the tire, so you will feel that your pump is getting hot, isn't it? Because you are compressing air. You compressing air, you are forcing it to come together and hit each other much frequent. So that is going to increase your temperature. So the particle in the air will hit each other very frequently and will generate heat. So that is the problem. So when you have enough heat, then it might combust the fuel air charge inside your combustion chamber. So like lower grade fuel will evaporate easily, and it will be combusting at lower temperature. For high grade fuel, it is heavier and it will burn at a higher temperature. So that is the problem with the high compression ratio. It is only using high grade fuel because it is heavier. It is what do you call it? It will combust at a higher temperature. It is not easily combust. But for lower grade fuel, you can have the combustion happen at a lower temperature. So that is why if you have low compression ratio, there should be no problem for it to prevent self-combust. But if you are using high performance cars with high compression ratio engine, then the engine can easily start the combustion before the spark plug can fire because of the greater compression that will generate enough heat to combust. And so that is one problem with the compression ratio. But high compression ratio means power, very good power. But the downfall is it is only using heavier fuel. Okay, that is for high compression ratio. But now you have a turbocharger. If you have turbocharger, are you increasing the mass inside the air? In the mass of air inside the cylinder? Yes. Then when you compress, more air is there. When you're compressing, more particles will hit each other and they are going to create more heat. Then you will generate enough heat for the fuel air charge to self-combust, which is very bad. You want to have the combustion occurring at the spark plug firing. But now it is firing, it is combusting even before the spark plug can fire. So that is very bad. You don't want that to happen. And so always Follow the manufacturer's recommendation. If you don't follow, then you will have detonation. Because why? You have pre-ignition. Why? Because the engine start combusting before the spark plug firing. Why? Because you generate enough heat. Why you generate enough heat? Because you are compressing at a higher compression. Or you can have too much air inside, being compressed already, and then you add on with the higher compression engine, you are going to generate enough heat much earlier to start the combustion. And so that is going to cost you a lot of wasted energy for that detonation.